The hydrologic cycle is the circulation of water between reservoirs and different states of water. This cycle ensures that water is continuously shared within the Earth's system between the atmosphere, hydrosphere, cryosphere, lithosphere, and biosphere. In this video, we'll explore the major transformations and fluxes of water between reservoirs, as well as direct and indirect human impacts on these. We'll then take a deep dive into the importance of submarine groundwater discharge in linking the biogeochemical cycles, water and nitrogen. This involves feedback loops and major connections with coral reef ecosystems. There are three states of water: water vapor, gas, liquid water, and solid ice. Surprisingly, when water changes into a different state, its chemistry does not change and it is still the same element H2O or dihydrogen oxide. The major components of the hydrologic cycle are its unique reservoirs and fluxes. Water is stored in various reservoirs which balance water availability throughout different ecosystems. The oceans are the largest reservoirs, containing 97.5% of Earth's water, so that only leaves 2.5% for fresh water. If we break down that fresh water, 79% is frozen on ice caps and glaciers, and 20% is stored underground. So that leaves only 1% for surface water, which is mainly stored in lakes and soils, followed by water vapor, living organisms, and rivers. Water can spend a certain amount of time in a reservoir before moving on to another. This is called the residence time. The average residence time of water in the biosphere is the shortest, at around 1 week. With longer residence times, water can spend around 10 years in lakes and an impressive 4,000 years in oceans. The highest residence of water is when it is frozen in glaciers and permafrost in the cryosphere, which can last between 1,000 to 10,000 years. So how does water travel between these reservoirs? This is through fluxes. The main fluxes in the hydrologic cycle are evaporation, condensation, precipitation, runoff, infiltration, percolation, and transpiration. Evaporation is the transformation of liquid water into water vapor. The main mechanism that drives this process is an increase in temperature energy, which forces the bonds that hold the water molecules to break. This can be from the sun's solar energy from above or geothermal energy from below. Other factors that can affect the rate of evaporation are wind and water density. Condensation is the transformation of water vapor back into liquid form. The mechanism that drives this process is called the dew point, which causes the air to become saturated with water depending on atmospheric temperature and pressure. You can see this in clouds, mist, or fog. This also causes droplets to form around cold surfaces as morning dew. Precipitation is when either water as a solid or liquid falls, for example snow, hail, or rain. The main mechanisms driving this process are condensation and gravity. Runoff is when precipitated water flows down land surfaces into reservoirs, replenishing them. The mechanisms involved in runoff are gravity, incline, and topography. Infiltration is when water is absorbed into the soil. The rate of infiltration depends on the porosity and permeability of the soil. Percolation is the movement of water through the layers of soil. The main driving mechanisms involved are gravity and capillary forces. Transpiration is the process by which plants release water vapor. This mainly occurs through the stomata, which open to exchange carbon dioxide with oxygen during the day. Water enters the atmosphere in the state of water vapor. Water vapor is crucial to Earth's climate because it is a primary greenhouse gas in the atmosphere. Water vapor determines a region's humidity and regulates its temperature through absorbing or releasing energy in its different states. When solar energy acts on the water cycle, it drives wind and weather patterns in the atmosphere. This energy in the water cycle can disturb the atmosphere and create major storms like hurricanes and typhoons. The availability and distribution of water is vital to life. Organisms like plants and animals use water for metabolism, then release water through transpiration or respiration. The hydrologic cycle is important to the lithosphere as it shapes landscapes through erosion, sediment transport, glacial movement, weathering, and aiding soil formation. And of course, the hydrologic cycle is central to the cryosphere of frozen water and the entire hydrosphere, encompassing all of Earth's water in all of its states and its interactions with the different spheres. Humans directly impact the hydrologic cycle by exploiting surface water and depleting aquifers, changing the flux rates and water distribution throughout the reservoirs. Humans mainly withdraw water from reservoirs for agriculture and irrigation, industrial use, sanitation, hygiene, and drinking water. Humans also directly impact the natural flow of water through reservoirs in the hydrologic cycle by constructing landscape modifications such as dams and wells. When groundwater is pumped excessively from wells, it can cause saltwater inundation, adding salinity to the freshwater reservoir. Humans also indirectly impact the hydrologic cycle when processes like mining, urbanization, and agriculture cause toxic runoff, water pollution, eutrophication, and groundwater contamination. Humans also change the composition of the atmosphere when industrial factories and machines output greenhouse gases like carbon dioxide and pollute air quality, increasing the occurrence of acid rain. Let's dive deeper into the mysterious world of groundwater. Groundwater occurs when water infiltrates through the ground and saturates the spaces between sediments and rocks. Groundwater discharge occurs when water moves out of the ground and into a surface reservoir, often because of landscape topography and changes in altitude. Submarine groundwater discharge is when this groundwater flows into the ocean. This process has a crucial role in linking biogeochemical cycles, especially connecting the hydrologic and nitrogen cycle. When the groundwater enters the ocean, it brings important micronutrients to the coastal ecosystems. The Great Barrier Reef receives approximately 1/3 of new nitrogen inputs and 2/3 of phosphorus inputs from submarine groundwater discharge. Moderate amounts of this nutrient loading can enhance coral growth. Submarine groundwater discharge can also enhance primary production by benefiting microbiological communities and benthic animals, including mussels. However, excess nutrients from submarine groundwater discharge can be detrimental because too much primary productivity causes too much dissolved oxygen to be consumed, and groundwater does not replenish the oxygen because groundwater is mainly anoxic. This can contribute to eutrophication and hypoxia, which drive a positive feedback loop that further worsens the oxygen conditions. However, there is a negative feedback loop that activates when the nitrogen to phosphorus ratio reduces and limits nitrogen, which decreases the organic matter and inhibits the growth of cyanoprokaryota and phycophytoplankton, restoring balance to the ecosystem. In summary, the hydrologic cycle is interwoven within the greater Earth system and connects the spheres in all of its forms.